In this video, I will go over discussion quiz number 4. Our first question here is a Gauss's law question. An electron is placed at the center of a tetrahedron, a platonic solid made up of 4 triangles. What is the net electric flux passing through one face? When asked a question about electric flux through one face, the first thing we want to do is calculate the total net flux through the entire surface. We'll use the charge enclosed side of Gauss's law. Since there is one electron at the center, the net flux through the entire surface is minus E over epsilon naught. Remember, that would be the net flux through any closed surface surrounding a single electron. Next, we want to check if the flux through the face in question might be 0 because the electric field and the area vector are either 1, everywhere perpendicular on the surface, or 2, a balance between positive and negative such that it will be 0. Now, due to the symmetry of the tetrahedron, the electric flux through a single face will not be 0, since the electric field points radially inwards towards the electron and the area vector always points away from the electron. Now that we know that the total flux and that the flux through the asked face isn't 0, we can use symmetry arguments and counting to get the answer. Now, because the electron is at the center, no face of the tetrahedron is special. Thus, each face will have the same amount of flux. Since there are 4 faces, each face will allow 1/4 of the total flux. Thus, our answer choice is B, minus E over 4 epsilon naught. Now, our next set of questions here is about the electric potential. Now, in our situation, we have a charged object with 1 nanocoulomb of charge. We have 2 positions in question, position A, which is 1 centimeter away, and position B, which is 3 centimeters away. So we want to calculate the potential at points A and B, and calculate the potential difference between A and B. Now, the electric potential at distance r from a point charge Q is given by the following formula, 1 over 4 pi epsilon naught Q over R. So all we need to do here is plug in for Q and for R. Q is the value of the point charge, 1 nanocoulomb, and R is 1 centimeter and then 3 centimeters. And finally, to calculate the potential difference, we'll just subtract the 2 answers. Now, the question wasn't clear exactly should you do A minus B or B minus A. We'll think about the importance of that in the next question in part D. So our answers here are about 900 joules per coulomb. Remember, joule per coulomb is a volt, and 300 joules per coulomb, and a potential difference is 600. Next, you want to calculate what the potential energy of a proton is at points A and B. Now, according to the way electric potential is defined, the electric potential energy of a charged particle Q at a location with potential V is given by the following formula, U equals Q times V. Now, the charge on a proton is 1 elementary charge, 1.6 times 10 to the negative 19 coulombs. So all we need to do is plug it into our formula and calculate the 2 potential energies. Next, we want to figure out the speed at point B of a proton that was moving to the right at point A with the speed of 4 times 10 to the 5 meters per second. Now, we've already calculated the potential energy difference between A and B, and now we want to incorporate kinetic energy. So to find that speed, we'll use energy conservation. Now, energy conservation tells us that the change in the kinetic energy plus the change in the potential energy will equal 0. In other words, the kinetic energy final minus kinetic energy initial will equal our change in potential, minus the change in our potential. Now, our kinetic energy formula is 1/2 mv squared, and our change in potential will be delta U equals E times delta V. So I plug in that information, and I want to solve for a velocity final. So I move some things to the other side, divide, take the square root, and make a few cancellations, and I end up with this final formula here. Now I just plug in what I know, and I get an answer of 5.24 times 10 to the 5 meters per second. Now, my final question here is to consider a slightly different situation, position C and D. You can see how C and D relate to the original A and B in question 2. Now, a proton is going to start at position C, moving it forward times 10 to the 5 meters per second. It's going to follow a curved trajectory. It's going to end up at position D, and we want to calculate that new velocity. Now, the key to solving this problem efficiently is to recognize the similarities with the previous question. The particle has the same initial speed and the same change in potential. Thus, no new calculations need to be computed. It's the same final velocity. And that's the beauty of conservation of energy. All that matters is the beginning and end points, not the path it takes in between to get there.